All right, so real quick, I just wanted to review from last week how to go from a rectangular coordinate to a polar coordinate. This will remind us of some of our formulas we can use. So our four polar equations are x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and tangent of theta equals y over x. So any four of those are fair game when we're playing around with polar coordinates. So when I look at the point negative 3, 3, I'm going to think about what quadrant that's in first, which is in quadrant 2. Now negative 3, 3, like I can see is actually going to be a 45, 45, 90 triangle. So I can just use my knowledge of like this being a 45, 45, 90, this is 45 degrees. And then the angle to get there from 0 would be 135 degrees, which is 3 pi over 4. And then I can just use my Pythagorean theorem to solve for that third side. So Pythagorean theorem will be x squared plus y squared equals r squared. X is negative 3 squared plus y is positive 3 squared equals r squared. So we get 9 plus 9. And then we square root. And we have to remember the plus or minus. So we have r equals plus or minus. Now 18 is 9 times 2. So the square root of 9 is a 3 on the outside, but the 2 stays inside the square root. So we have plus or minus 3 square root of 2. Now, since I determined just from my sketch that the angle is 135 degrees, and then if I'm pointing, looking at quadrant 2, I would then move positive radius to go with that 3 pi over 4. So my r theta point is positive 3 square roots of 2, comma, 3 pi over 4. So just a slightly different way of getting to that same answer that Amplify wanted. An equivalent point, though, if I wanted to work with a negative radius, I'd look at the angle that's pi radians off from that, which is negative pi over 4. So if I was using my formula, tangent theta, that would spit out negative 45 degrees, which is negative pi over 4 radians. With the negative pi over 4 radians, we would have to walk backwards to get into quadrant 2. So the other r theta point would be negative 3 square root of 2 and negative pi over 4. This is what we would get, especially if we were doing it on web work. Web work adds the qualification that theta has to be between negative pi over 2 and positive pi over 2. So we'd be stuck using negative pi over 4. And then the radius to go with negative pi over 4 has to be negative 3 square root of 2 to move us into quadrant 2. So you will have one of these on the test where you're going to be given the xy coordinate and you have to calculate the r theta coordinate. And it's going to have the same restriction as web work, that theta has to be between negative pi over 2 and positive pi over 2. And there's several problems in your homework, and then there's a couple of problems in the exam 3 review. And we'll go over the review on Thursday, but this is one of the ones that we're going to want to make sure we hit. So what questions do y'all have on the way this played out? The formulas, the 2 different ways to write the point. All right, so what we're going to look at next is we're actually going to start looking at polar equations, and we're going to look at how they graph. Well, they're not in the way there, so I'll just leave the equations. Oh, real quick while I'm thinking about it, hold on. Let me screenshot this. All right. So now we want to transform this weird polar equation back into a rectangular equation. So any of our 4 polar equations, polar formulas, are fair game to help us out here. Now, I don't have just a r equals and just a theta equals. I've got something a little weirder. But whenever I see a sine theta or a cosine theta, I always want to think back to the x equals and the y equals formulas. So that formula, if I had an r next to the sine theta, then I could trade out r sine theta for y. So that's what I'm going to do first. So I have r equals 4 times the sine of theta. And I'm thinking it'd be great if I could just sneak an r multiplied to the right side. And I can do that as long as I do the same thing to both sides. So now I have r squared equals 4 r sine theta. And now I've got stuff that actually shows up in my formulas. So that r sine theta, that's y. And then I still have the 4. And now r squared, that's the same as x squared plus y squared. So that's what our first hint was first multiply both sides of the equation by r, then you should recognize some substitutions, and we get that equation. And the equation, if we completed the square, could be rearranged, and we'd see that this is the equation of a circle with the center moved off of the origin. So when we start with a polar equation and we're trying to go back to the rectangular equation, it gets a little weird. We have to try to force some pattern matching to occur. But we can still do it as long as we keep in mind that I really do want to pattern match it to the formulas. All right, now we need to make it disappear. So a polar graphing demo. So what I have here is an A slider. I'm going to slide it all the way to 0. So we have our equation r of theta equals 4 sine theta. And then underneath it, they're saying only graph it from 0 to a. And then we created an a sine slider. And then r of a is just telling us what the function value is for the a value. So a here is in terms of radians. So I can see as I move the slider, the graph is graphing. And when I get to like the 1.57, 1.57 is the decimal for pi over 2. And we can see at pi over 2, r of a is really close to 4. So yeah, it makes sense at pi over 2, I'd be at 4 because sine of pi over 2 is 1. And then I keep going and I get to 3.1, a little past it, but it's real close to 0. So at pi, sine of pi is 0. So it makes sense at pi it would be at 0. And then if I keep tracing it, like it makes the circle again, but take a look at the r values as I slide it through. So my r value starts at 0, and then it's positive, 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 and it goes all the way up to 4. Then it starts coming down. It's still positive numbers, but it goes all the way down to 0. Now, if we think about our graph of 4 sine theta, that starts at 0, goes up to 4, comes back to 0, goes down to 4, and then comes back to 0. So now, after 3.14, now we're in the negative. And you notice it's got this dashed line on the graph because that's the angle we're looking at. We're in an angle that's down in quadrant 3, but our radius is negative, so it plots the point back on the circle we already traced. So it's tracing the same circle again. And eventually I get around here, around 4.7 is where it's negative 3 pi over 2, or sorry, positive 3 pi over 2, but the radius is negative 4. So that's why we're at the top of the circle again. And then it continues until it gets to 0 again. Now, if we open the table here, these are our unit circle values and the function values, the polar equation values. Now, calling it a function gets a little weird in a polar sense. It's a good thought process, but it's weird. And I can actually turn these points on. So these points, these are the points for the graph of 4 sine theta in the xy plane. But each of these points correlates to a polar point on this circle. And then if I turn on my x squared plus y minus 2 squared equals 4, I get that same circle. So typing in r of theta and typing in the equation in terms of theta, and then having this 0 less than theta less than a, and then just being able to slide through all the points, this is a really great way to graph polar equations. Because one of the big things about polar equations is you want to understand how the graph moves through the points, like what direction it does. So if I was just going to freehand draw this circle, like I would probably draw it clockwise because I'm right-handed and that's how my brain just like translates it. But if we look at the way the point traces around, it actually traces around counterclockwise. So just more like an interesting note there. Now you're not going to have to graph by hand on the test. And you really don't even have to do it for the homework for this. You can just like BS your way through the 5.4 homework, which is what I highly recommend doing. All right, so our next question is saying transform y equals 3x plus 2 into polar form. So this is in the xy plane, this is just a nice little straight line that has a y-intercept of 2. To graph this in polar, it's going to look really weird. So I'm going to write the equation first. Y equals 3x plus 2. Now, one of the nice things is if we're going to transform this into polar, when we start with xy, we can just make the straight substitutions for x and y. So in place of y, I'm going to write r sine theta. And in place of x, I'm going to write r cosine theta. So I just made those two direct substitutions for x and y. Now, technically, I have a polar equation, but that's not one of our answers. And I can't type this into WebWork. WebWork will be like, no, I hate you. So what we need to do now is we need to get r by itself. So my r shows up in more than one spot. So I'm going to get all of my things with r on the same side of the equation. So r sine theta is already on the left. 3r cosine theta, I'm going to minus that to the other side. So I have r sine theta minus 3r cosine theta. And this is just equal to 2 by itself. Now, both of these things on the left have an r. So I factor out the common r and write my leftovers. And then to get r by itself, I just divide by the weirdness. So r times ugly mess, so I divide by ugly mess. And r is 2 divided by sine theta minus 3 cosine theta. There it is. And we get a very excited baby. Or toddler, I guess. So this is the kind of thing we ask you to do on the test as well, is to take a rectangular equation and transform it into a polar equation. So there's a few questions in the homework that ask this and a few in the exam review. So what questions do y'all have on how this played out? All right, let's see our next one. So these next slides are just to show you some of the cool graphs you can get. So this is screenshots from the book. So we have equation formats that make particular graph shapes. So a cardioid is because it's a heart shape. And this requires that we have a plus or minus a cosine theta or a plus or minus a sine theta, where a is positive. But it has to be the same. Now, if that a is not the same, we have an a and a b, where the b is smaller than a, we get what's called a limacon without an inner loop. If we flip which one's bigger, then we get this weird inner loop. So you can see like these three shapes are kind of closely related, because if I erased the inner loop, like this would look kind of like a heart. And I can see this one has like a dimple that's almost trying to be the point on a heart. And then we get a lemon skate, which is like a sideways infinity. And then we can have a rose with number of petals. So if I have 3 theta, I get 3 petals. If I have a sine 2 theta or a cosine 2 theta, I get 4 petals. So now I have right now the graph of r equals cosine 1 theta. And then there's a button to change n. So now I have cosine 2 theta, 3 theta, 4 theta, 5 theta, 6 theta, 7, 8, 9, 10. And 10 has 20 petals. So as n changes, we get more petals. And then if I look at the symmetry, like it's top bottom symmetric, top bottom symmetric. So all of these graphs are symmetric across the x-axis. Some of them are symmetric across the y-axis as well. But we're just typing in what we see. No right or wrong there. Now, when we look at different sine of n theta, now I can see sine of 1 theta is symmetric across the y-axis. It's left-right symmetric. And then as I change n, it keeps the left-right symmetry. But it also does the same thing. As n increases, we get more petals. But all of our sine graphs are symmetric across the y-axis when we're looking at a polar graph. So cosine graphs are symmetric top bottom. Sine graphs are symmetric left right when we're looking at polar. Now here, as we change A and B, we get a lot of different crazy shapes. But we saw what happens on all of these descriptions earlier. I'm trying to find one where A over B is bigger than 2. I don't know if we get one. No, I think they're all 3, 4, and 5. So that's okay. We don't have to fill in anything here. It's more just like, look, graphs do pretty things. All right, this is the graph of a lemon skate. The A value is that 3. So when I hit change A, sometimes it changes, sometimes it doesn't, but it changed from 3 to 6. And now I can see that the end points, the furthest points on my infinity, are at 6 and -6. Then it's back to 3 and -3, 5 and -5. So that value just determines how wide the lemon skate is. All right, now this one is a fun slide to play with. So my Cartesian graph, this is if I had XY points. And I can move these points up or down. And it's going to create different shapes on the polar. So I'm just kind of picking every other one, but I could like, I don't know, do a weird shape like that. But it just like lets you see if you set the values, what does it do to the shape? And then this one is really wacky. So what I have here is, it's like the previous slide. This is the Cartesian graph. But when we click show polar version, it's going to show you how it takes the Cartesian graph and turns it into the polar. So it's a really neat animation. So it flips it along the diagonal, and then it rotates the graph grid. So if I reset it again, I can see here the first part, those are like the wing edges and the bat head. And then the second part is the bat tail. Now over here, we've got like a kind of point and then a weird curve. So it's going to do the diagonal flip. And then that point that starts on the right axis is going to stay, like after the flip, this point that ends up on the bottom of the grid after the flip is going to stay there, and all the rest of the grid gets rotated. So this is just some of the weird things that you can do with polar graphs. All right, so what I want to look at now is actually go dig into the web work, particularly section 5.4. So I just want to show you guys like what these questions look like and how we can answer them. So we have the equation r equals 3 cosine theta. Now to figure out which equation this is, I could plug in some theta numbers, get the r numbers out, and then plot those r theta points to figure out which one is correct. Particularly if I can figure out this 3 point at pi over 2, like that's what it looks like. If I plug in pi over 2, cosine of pi over 2 is 0. 3 times 0 is 0. So a radius of 0 is our origin. So that's a point on all of these graphs. So pi over 2 was not that helpful. Let me write that down, though. So when theta equals pi over 2, r equals 3 cosine pi over 2, which is 0. 0 pi over 2, this is the origin, which is on all of the graphs. So pi over 2 didn't help us distinguish the graphs. So since this is cosine, though, the cosine of 0 is not 0. So if I plug in 0 degrees or 0 radians, r equals 3 times the cosine of 0, that gives me 3. So the r theta point is 3 comma 0, which is to the right on the graph, which is graph C here. Now, the only reason I go to the effort to do this by hand is because in the past, we have given one of these on the final. And I don't know if we're going to do that on this final again. But yeah, I come down here and I type in C, check, and it is happy with C. Now, as I progress through, the graphs start getting more interesting. So 3 minus 3 cosine theta, I can plug in 0, but that'll be 1. 3 minus 3, I'm going to get a 0 again. And then pi over 2 will give me 3, but both A and B go through 3 comma pi over 2. So what I do is I sneak over here to Desmos. So we had 3 minus 3 cosine theta. Bam. That gives us the cardioid that's facing in this direction, which is A. And I liked A. So I could figure it out by picking numbers and plugging them in and seeing if that point appears on the graph. But for most of these, especially when the equations are getting kind of weird looking, so we've got a sine theta graph. So remember when we looked at the sine pedal graph, sine graphs are symmetric across the y-axis. They're left-right symmetric. So that means it's probably B or D. Now picking which one it is, again, we could pick numbers, but we can also just come over here to Desmos. And there it is. It's D. All right, so our next one, Limasan with a loop or without a loop. So it's probably B or C because a cosine graph is top-bottom symmetric. It's probably B. Then we got a sine theta. All of these are sine theta symmetric. Then again, I just type it over there, see which one it is. More loops. And then we get this one. So this is r squared equals cosine 2 theta. So this, if I try to type it over here on Desmos, r squared equals cosine 2 theta. It's producing nothing for the graph. So the way Desmos works, Desmos can't handle the squared there. So we're going to have to instead square root this side of the graph. And I'm going to do that with the 1/2 power. So when I do that, I get just the left, right, two petals, that infinity. But whenever we do a square root, there's also the possibility of a negative. So my positive square root gave me the infinity. When I turn that off and turn on the negative square root, it gives me the same graph. And that is very common in polar graphs. But going back to our web work, that is graph A. So this is one of the few equations that you can't type directly. You've got to get it in an R equals format. But Desmos can still handle graphing it. You got to get it R equals. Again, we got to get it R equals. We've got 4 sine 2 theta. And that gives us a infinity that's centered around the 45-degree line, which is D. And then 6 cosine 3 theta, this is actually going to be A or B. The cosines are top-bottom symmetric, so it should be A. So all of the questions in 5-4, you can just work by typing it in Desmos, getting a look at it. You could pick theta numbers, plug them in there, and see what you get, but you'll have to plug in stuff like pi over 4 or pi over 6 and really think about where is that point going to be if you do it by hand. Now, on the test, we're not going to have one of these. And when we've done this one on the final, it literally looks like these questions. Not, well, here, let me it looks like one of these first two. Well, this first question. It may be sine theta instead. The number might be a little different. But it's a very basic polar graph, and you're just figuring out which one it matches. You're not having to graph it by hand. It's a multiple choice. Which picture goes with the equation? So questions on the polar graphs, like how to do that homework, how it might look on the final. All right. So let's put a pin in that. Ooh, yeah, question. Ooh. Yes, there will be a web work review for the final, like the tests, and you will get 10 bonus points for doing it. Like if you get 100 on it, you'll get 10 points. If you get like a 92, you'll get 9.2 points. All right, so we could look into like the web work on 5.3, but before we do that, did you guys have questions about anything that's due today? There's a writing assignment that's due today on law of sines and law of cosines. Um, we could look at that if you wanted, or any of the old homeworks as well. All right, well, I'm just going to load up the polar stuff just so we can kind of see the format here. But if y'all are like digging through or looking at the writing assignment and you're like, oh my God, I have no clue how to start number 3, like we can take a look at it. So feel free to interrupt me if you realize there is a question you want to cover. All right, so this is an applet question, so this can be a pain to load on some of your computers. They're giving us the point -2, comma, 19 pi over 3. All right, sure. So first step is just figuring out where 19 pi over 3 is. So 19 pi over 3 is way bigger than 2 pi. So let's see. 3 goes into 19 6 times with some left over. So that is 3 2 pi's. So I'm going to take off 6 pi. And just to kind of illuminate how I got that, I was like 19 over 3 is 6.33, and 6 is 3 times 2. All right, so 19 pi over 3, and then 6 pi, I'm going to multiply it by 3 over 3 as well for a common denominator. So minus 18 pi over 3 gives us an angle of pi over 3. So we're really plotting -2 pi over 3. Now, pi over 3 is 60 degrees. So that's this line here. So we're on the pi over 3 line, but we want to go to -2 for the radius. So I'm going to take my point, click it, and I'm on this line, but I want to go down here to the -2. Now this can be really annoying. So we can zoom the grid in some and just try to get it really nicely on that crosshair. And then we hit check answer, and it is happy with what we did. So I had to do a little bit of extra work just to figure out where that angle really was. And then I had to think about the backwards radius. Looks like this one's more of the same, but this is -pi because it's 6 over 6, but it randomly picks the two numbers there. So it might end up being a little different. Yeah, let me flip the share to OneNote because I took a screenshot. So the angle, they told us 19 pi over 3. So I was trying to figure out how many 2 pi's can I subtract off of 19 pi over 3 because it's way bigger than 2 pi. So I was just thinking like 19 over 3 is 6.33. So this is 6 pi's and a little bit more. And then 6 is the same as 3 times 2. So there are 3 2 pi's that I can subtract off of this. You can also, though, just on the calculator, start with 19 thirds and then go -2, -2, -2. And then if you do it an extra time, you'll get a negative fraction. So then you add 2 back, and that's the fraction that it's equivalent to. So if you -2 3 times from 19 thirds, you'll get 1/3, and then you just write the pi back in on top. But that's how I knew it was 3 full rotations I was subtracting off. But when I was crunching the numbers by hand, I did the times 3 over 3 to get the common denominator. So it's 3 times 2 times 3 on top. And it's technically over 1 on the bottom. So that's where we get the 18 thirds. And then 19 minus 18 gave us pi over 3. So does that make more sense? Like how I knew to pull off that many rotations? This is the same calculation we did when we first learned about coterminal angles, like at the beginning of February. So it's just been a hot minute since we've had to do it, but we have done it before. So did that help, or was it too much talking too fast? It's okay if it wasn't enough. Okay. Okay, let's see problem 3 here. Yeesh. And the reason I went yeesh on problem 3 is because it's really 6 problems at once. So our 1 through 6 are polar points, and our A, B, C, D, E, and F are XY points. So let's just label those. These are our theta, and these are XY. So they're just wanting us to take each of these polar points and figure out what the XY points coordinates are that go with them. And this direction is actually very straightforward. We can just use the x equals r cosine theta, y equals r sine theta, and we'll directly get those numbers. So let's see which guy is like weirdest. Maybe number 4 here. So x will equal 1 cosine negative pi over 3, and the y will equal 1 sine negative pi over 3. So the cosine of normal pi over 3 is 1/2, and the cosine of negative pi over 3 is still 1/2. But the sine is negative square root of 3 over 2. So that is E with our 0.5s in there. Now, y'all's order might be mixed up a little, but it is probably all of these same ordered pairs. But we're just using those basic polar r cosine theta and y equals r sine theta formulas. So a little tedious, but just extra practice using the formulas, extra chance to write them down so they just stick in your head a little better. Now, the odds of you having to actually like use polar coordinates that much are actually like very rare in math classes. We use them a little bit in Cal 2, where we talk about doing derivatives and antiderivatives of polar graphs. And then it can show up in Cal 3 or sort of in linear algebra, depending on how you're looking at it. But for applications, like I said, like spherical coordinates are like the way a lot of video games process visual changing of the display in first-person games. All right. Question 4 is kind of similar, but a little bit different. So these are two polar points that we're trying to decide if they're the same or if they're different. And whether they're the same or different, like depends on what the angles are, if they're pi radians apart or not. So one of the ways to do this is just to flat out like plot both of the points on Desmos and see if they're the same. Another way, though, is to take both points and run through the XY calculation. Because if they're the same, then the X and Y coordinates will be the same. Because there's only one X and one Y that'll get us to that location. But on some of these, we can actually reason through. Like C here is a very special case. 0, 4 pi and 0, 4 pi over 4. The radius here is 0. When the radius is 0, that point is on the origin. So these are the same point. But we could put 0 and any angle, and it would be the same point. So I could say 0 and 27 million pi, 0 and negative 3.4 pi. Like, it doesn't matter what the angle number is. The fact that the radius is 0 makes those always the same point. Because you're basically just sitting at the starting point and spinning in an office chair. It doesn't matter which way you're looking because you didn't move the chair. All right, so if we take a look at like the 5, 38 pi over 3, and negative 5, negative pi over 3. So my x coordinate 5 cosine 38 pi over 3. I'm just going to type that on the calculator. I do want to make sure that my calculator is in radians mode because my angle is in radians. So boop, radians mode. 5 cosine 38 pi divided by 3. And this gives me negative 2.5. Now I'm going to check if the other coordinates, the negative 5 cosine negative pi over 3, if those give me the same number. So, oops. Negative 5 cosine negative pi over 3. And that does give me negative 2.5. So this means maybe. Now we check the y's. So, whoops. So now we check 5 sine 38 pi over 3. And this is going to be some ugly square rooty number. And really what we're looking for is we're looking to make sure they're the same square rooty number, but really the same positive or negative. So 5 sine 38 pi divided by 3. .33 blah, blah, blah. And then negative 5 sine negative pi over 3. And I do get the same positive 4.33. All right, so that one is true. So that's just how to do that, is just using our same formulas and just checking to see if both the x and the y's are the same. You can also think through plotting the points and see if they're the same. Sometimes they are, sometimes they aren't. All right, and then it's just practice doing conversions from rectangular to polar and some practice with here's weird equations, convert them to the alternate form. But I remember from law of cosines, there was a question in here that somebody asked about that I never drew the drawing for. Yeah. So in 5.2, problem 8. So your 5.2 homework that's due today, the last half of it is all word problems. So our weird diagram here, we've got a tower located on a hill, and the hill is a 34-degree incline to the horizontal. A guy wire is to be attached to the top of the tower and anchored at a point 98 feet uphill from the base of the tower. We need to figure out how long the wire is going to be. So I'm going to sketch in some lines here. All right, so I drew the height of the tower and I dropped that all the way down to the base, the horizontal line. So that makes a 90-degree angle in there. So I see I have a little right triangle, and then I have my big wonky triangle, the upper right triangle, that I actually have to use to solve this problem. So in my wonky triangle, I know I've got 98 feet and 113 feet, but I need to know what the angle between them is. And they're asking me to figure out what that length of the wire is from the top of the tower to the hillside. So that's my unknown that I want to solve for. So to use law of cosines, I need to know that angle. So now we've got to use some geometry to figure out that angle. So those two lines that I drew, you see how they intersect? The way two straight lines intersect, the two like small angles, they look like they're the same, and the two big angles look like they're the same because they are the same. So regardless of which way I rotate my lines, as long as they're straight lines, those what we call opposite vertical angles are equal. So those two angles are equal. So the angle I need to know is equal to this third angle in the right triangle. So I have the 34 degrees and I know 90 degrees, so I can figure out that third angle. So I'm just going to call it theta. So theta is going to be 180 minus 90 minus 34. So 90 minus 34, because 180 minus 90 is 90, is 56. So in our triangle, the angle in between the two sides is 56 degrees. So these are the numbers that you have to use for the law of cosines. And then they tell us to round to the nearest tenth. So our law of cosines formula is c squared equals a squared plus b squared minus 2ab cosine gamma. That's how it'll be written on the test. So I need to label my triangle so it matches my formula. So the angle I know is 56 degrees, so that angle has to be gamma. Or we could call it angle capital C. Gamma goes with capital C. So that means the side we're looking for has to be side C. And that means the 113 and the 98 are A and B. And it doesn't matter which one you call A and which one you call B, because the formula works either way. So I just usually go with like left is A, right is B, or, you know, whichever, because it's not a right triangle. So, and now I can use my formula. So we'll have C squared equals 113 squared plus 98 squared minus 2 times 113 times 98 times the cosine of 56. All right, now I was just doing polar calculations. I was just typing in negative pi over 3 in my trig functions. So my calculator right now is in radians mode. Now on my phone, it's got a very nice like RAD on the side. It's very obvious when it's in radians mode. But on y'all's calculators, it's more subtle. So it is really easy to run this calculation in the wrong mode. So I'm going to do that just to kind of show you what it can look like. So 113 squared plus 98 squared minus 2 times 113 times 98 times the cosine of 56. So I got 3,475.88. And that seems way too big. So now I'm going to square root it. And I got 58.95. And I'm putting the question marks here because I'm doing this on purpose. I know this is the wrong number. But looking at the problem, like 58 actually seems kind of reasonable. Like 56 seems like it's probably the smallest angle. So that might actually be kind of close. But I'm going to go back to my original calculation and change it to degrees. So let me just make a note. Like this is rad mode. And then down here, this is our degree mode. We got 9,987.9955. And now I'm going to raise that to the 0.5 power. And I get 99.939. And they said rounded to the nearest tenth. So we're going to type in 99.9. Now, sometimes if you don't remember to change your calculator mode, you'll get a negative number and then it's like quite obvious, like, oops, I'm in the wrong mode. But it turns out 56 radians is not unreasonable instead of 56 degrees for the way the calculation worked. But it is the wrong thing. So if you're working on some of these word problems, these law of cosines problems, especially if you were moving around in your homework, like double check that you're in degrees mode on your calculator. The real place where this is a problem, though, is the exam. Your homeworks, your web works for the most part, you're going to do like all of a section in degrees or all of a section in radians. On the test, though, those sections correlate to single questions. So whenever you're moving between questions on the test, you're going to have to switch between degrees and radians mode. So just, try to be mindful of that. All right. Are there any other questions from any of the sections that you guys want to take a look at? Yes, when we do the review in class, I can do that. Um, Like the big one is when we do the polar coordinates, that's where we're in radians. All the rest of them are, it either doesn't matter or they're in degrees. But yeah, when we do the review on Thursday, I can remind you as we go through, like, depending on what calculations we're doing. Yeah. All right. Well, if y'all don't have any more questions, I'm going to stop the recording.